take a look at the modules for this particular experiment. And you guys are going to see that we have gas law right here. Complete via Canvas. This is the gas law simulator. So what you guys will need is you will need to access this site right here. Yeah, this is the website right here. So I'm just going to copy that. Here it is. Okay, so you guys should see that. So I'm just going to walk you through this so that you guys can see what's going on here, and based on how to operate this device. So first of all, you have gas A or gas B. You can switch the gas depending on what you click on. Okay, you can have both gas on or just one of the gas. Let's see if I can increase that. Okay, so in this particular case, I'm going to just do gas A, and that's what the direction calls for. This right here allows you to pump gas in. So notice that as I pump gas in, the pressure changes right here. Okay, this will release the gas. Okay, so that now there's no gas, and I can pump in gas so that the pressure changes. This right here will change the temperature. I can heat it up, and then I can stop it or cool it down. And if I click on it, I can adjust it that way, and then you can read the temperature right here. Okay, heat, double click. So again, you've got the pressure here by that pump. You can release the pressure. You can pick the gas. You can change the temperature. And here's the volume. We can decrease the volume or increase the volume. And here are some data for gas A and gas B. And right now, all we have is gas A in there. So in this particular case, if you look at your data sheet, it says you're going to change the volume to about 300 to 400 liters. First, evacuate everything. Okay. Then we're going to change this to about, maybe we need to pump in a gas real quick. Oops. Okay. And then we're going to change this volume to about 300, 400 liters. So we're just going to increase this somewhere around there. Okay. Change the pressure to about 2.67. So to 2.0. So I'm going to pump this. Oops. Too much. And again, you guys are going to have to work this so that you're comfortable, because this is basically what you guys are going to be doing in terms of this right here. Actually, the red is what you do, and these right here is what you record. So let's go back to the data sheet. This is a volume pressure relationship. What we're going to do is we're going to set this temperature at 295. And sometimes it's hard to control this. So you have to learn how to double click. I'm going to do one pump here. Okay, just one pump according to the data sheet. Okay, and now I'm going to say that for this particular case, what happens to the pressure and the volume in this particular case. Okay, so in this particular case, I want to change the volume between 300 and 400. So this is it right here. Okay, that's it. Now put in the pressure, put in that value. So for whatever pressure you have, you got to write down the value. So I'm going to say that the volume that I've adjusted this to is 366. The pressure that I have in this particular case is 1.98. Okay, so that would be my first data point. And that's all you're doing in this particular first module. Now we're changing the volume to 500 to 600. So we're changing this to 500 to 600. Okay. So that'll be 566. And what is the, I'm going to put in here 566. You just typing this in. And what is the pressure? The pressure is 1.28. So the first part here, you're just gathering data. Okay, you're just gathering data. Here, you're changing the volume to between 800 and 900. And again, you're just doing this. Okay, type in the volume. Type in what the pressure is corresponding to that. Okay, and now you've got the data for that. You move on to the next module, because when you do the calculation, it's going to ask you to do calculation for all of this. This is the analysis. Okay, right here, table 1. This is table 1 right here. Table 1 says right here, when you increase the volume, look what happens to the volume. Okay, when you increase the volume, it goes from 366 to 566 to 886. What happens to the pressure? So this question right here, when you increase the volume, that's what you're going to check mark. Then what happens to the pressure? Does the pressure increase or decrease? Check mark that. Okay. Table 2. Table 2 is a volume temperature relationship right here. So what we need to do is we need 1 atmosphere, which is 1 pump. So again, we're going to go in here to this chamber, clear it out. Okay. We're going to do 1 atmosphere, 1 pump. There it is, 1 atmosphere, 1 pump. And now we're going to look at the temperature, 75 to 100. So I'm going to convert this temperature to 75, okay, to 100. Oops. You got to learn how to double click. Okay, so 85 is fine. So I'm going to put 85 right here. And what is the volume? The volume in this particular case is 209. You got to make sure that the volume is not locked. It's got to be able to adjust. So you got to unlock it. Otherwise, the volume is always going to stay fixed. So we want to see the volume temperature relationship. So you're going to type in here 209. The second is what happens when I raise the temperature to 125 to 150. So I'm going to raise this temperature. 145 is fine. And what is this volume? It goes up to 375. So I'm going to type that in. Okay. And now you go back to the bottom here and it tells you when the volume increases or decreases, you look at the trend, what happens to the temperature? Of course, we're changing the temperature, so you can certainly do this first and then look at that. But these are the 2 variables that are being changed for that particular sequence. Let's take a look at the third table so you guys can see how to manipulate that. Again, what I'm going to do is I'm going to exhaust this. I'm going to change the temperature to 70 or some convenient temperature, but I'm going to change that to about 70 right there. And I'm going to put about 1 atmosphere of gas. And in this particular case, 1 pump. Okay. Oops. I got 2 pumps. So let me do that again. Okay, 1 pump, 70. And now what I'm going to be doing is I'm going to adjust actually the temperature, and I'm going to be I'm changing the number of pumps. Look at the volume, 172. So for 1 pump, 70 degrees, 1 atmosphere, that's 172. That's correct. So the next is 2 pumps. So another pump. Look at the volume. Type that in right here. And then we're doing 3 pumps. Look at the volume. Type that right there. That's what you guys are doing. That this is what the simulation is. And then what you're doing here in this table 3, you're looking at the volume moles relationship. When we change the volume, when we change the moles, because every time we pump, we're changing the moles, what happens to the volume? Okay, does it go up or go down? That's basically what these are. You're looking at the variable parameters when the other two parameters are constant. So I'm going to skip 5 and 6. Okay, 5 and 6. This one, one pump, lock it at 600. When you lock this at 600, again, exhaust this. Okay, we're going to lock this at 600. Let's go with one pump. And then I'm going to increase this to 600. And sometimes, okay, 602 is good enough. Okay, and then we're going to lock it right there. Okay, so here we're varying the temperature. We're varying the temperature, heat it up, cool it down, and then figure out what the pressure will be based on that. That's number 4. Number 5, we're going to keep this at 500. Again, always exhaust the gas first. Keep this at, let's see, one pump. We're going to do one pump. Okay, we're going to keep the volume at 500, and that's going to be constant. Whenever we lock it, we're saying that it's not going to change. And if you can't get it as close to 500 as possible. Lock that. We're going to convert the temperature to 315. There it is. And now what you guys are going to do is you guys are going to change the number of pump and then record the pressure. Okay, so I'm going to skip 6. Let's take a look at 7. Calculate the universal gas law constant using the root mean squared equation. Now, in the gas law, we didn't do the root mean squared equation, but I do give you this root mean squared equation right here. I give you that. Okay, I give you this equation right here. So what do you need to do in order to calculate R? R is equal to the root mean squared parameter, URMS squared, times the molar mass divided by 3 divided by the temperature in Kelvin. This is the equation that you guys want to use, okay, in order to calculate R. How do we get the root mean squared temperature? It's right here. It's right here. RMS 1618 is what you would use, and that's what you would be recording right here in this graph right here. So what are we going to do to generate this graph? We're going to basically do one pump. We're going to set the temperature to K, and we're going to fix the volume at 1000. Okay, so the way you do that is, we're going to exhaust all the things. We're going to use gas A. I think we're using gas A for this right here. We're going to do one pump. We're going to do 1000 liters. And then we're going to fix the volume. 1000 is the maximum, so we're going to fix that. And then we're going to set the temperature to 10. So we're going to cool this down. Okay, 10 is the lowest. Here's RMS for A. So you just want to write that down. Okay, RMS for A is 288. What is R prime in joules per mole? Right here. R prime is RMS times the molar mass times 3 divided by 3 divided by T. So what is the molar mass for gas A? It's 3.0 grams per mole. Okay. However, you must use 3.00 times 10 to the minus 3 kilograms per mole in order for the units to be correct. Okay. So I tell you what the molar mass is. You can now plug it into this equation and calculate R prime. What is R double prime? It's going to be this equation right here. Okay. It's going to be this equation right here. And the difference between these two equations is that, so R is the universal gas law constants with different units. R prime, you use 3 times 10 to the minus 3 kilograms per mole to calculate that value. The URMS is found in the simulator. And then you divide by 3 and the temperature, the absolute temperature. Once you calculate that value, then you change the units of joules to liters atmosphere by dividing R prime by 101.3 joules. You can see that conversion factor right there. I give you an example right here. I give you an example right here of how to do that. So go ahead and read that, because this is an example of doing this. Okay, so what we're doing in the second part is we're just calculating the universal gas law constant. There's actually two values for the universal gas law constant. You guys saw the first value in chapter 8. The first value is 0.08206. The other one is, when we use it in joules, is 8.314. 8.314. So when you're calculating the first one, you want to use 3.0 times 10 to the minus 3 kilojoules per mole. That gives you R prime. Then to calculate R double prime, the second gas law constant, just take R prime, divide by 101.3 joules, and that converts joules to liters atmosphere. Calculating. That basically is it right here. That's what this is. You guys are basically changing 10 Kelvin. Remember that the volume is fixed. You're recording the pressure. So we're going to go next to, let's take a look at this. We're going to 100 Kelvin. So in order to go up to 100 Kelvin, we're going to heat this up. There, I got lucky. So at 100 Kelvin, the pressure is 0.25 and the RMS is 912 right here. Okay, 912. This is the average kinetic energy, 1.25 kilojoules per mole. You could record that as well. The next temperature is 300.
I'm sorry, Professor, can I ask a question, please?
Sure.
The average KE, the kilojoules over moles, you know, you said we could write that down. Where would we write that down?
Just write it next to anywhere here. I don't think you really use it, but it's nice to see that the kinetic energy is going to increase with temperature. Okay, so it's not really used in the equation, it's just provided for you.
Okay.
So that you can see the relationship there. So we're trying to get to 300. And again, it's tricky to get these numbers. You got to be quick with your mouse there. Okay, you got to like double click in order to like start it and stop it. So now we're at 300 here. We can figure, this is still one pump. This is still one pump. You can figure out the pressure here and you can read the RMS right there. Okay, so that's that. And same thing here, okay, except this one, you're using gas B. The second table here, you're using gas B. So let's exhaust this. Let's turn that off, turn this on, do one pump. Okay, I think it says one pump. And now let's bring this all the way down to 10. I think that's the lowest. And make sure that our volume is 1,000. I think that's the largest. And then lock it in. Okay. And then you just go through the same motion. You change the temperature, you record the pressure, and you record RMS. That's that table. And that pretty much is your lab. Okay, that pretty much is your lab. You just want to manipulate this. And then hopefully through the calculation, you guys are going to be able to see that PV equals nRT is consistent with the experimental results, or the experimental results always goes back to PV equals nRT. Okay, it always goes back to that. So here's gas A right here. This is gas B right here. That would be the second table over here that you guys are doing. Okay, gas B for 7B and gas A for 7A. I think there is one question down here where you guys right here determine the number of moles in pump 1. Use the R that you calculated. And the way you determine moles is PV equals nRT. You know what R is based on your experiment. You go back to you go back to here and pick one of these where you have the temperature, the pressure, and the volume. And now you have R, so you can calculate moles. Okay. Remember, PV equals nRT, so N equals PV over RT. So if you have, for one of these data points, or in fact, you can do the average, you've got a series of pressure for the pressure, the volumes are all constant, and the different R's, okay? R should be constant as well. Then you can figure out an average moles for the one pump, because I haven't told you that. I just gave you in the beginning that one pump, assume it's 1 mole, but you can actually calculate the exact moles for one pump. And you can do the same thing for 2 pumps and 3 pumps and show calculation. And that basically is your lab, okay? It's a lab where you're just going through the simulation, and the simulation is pretty accurate. That basically is it. And then just make sure that you know how to fill these data, and it will require you guys to play around with the simulator a little bit, okay? This will tell you the moles, this will tell you the temperature in Kelvin, this is the pressure, which is a function which generally changes when you adjust the number of pumps right here, okay? And this is your volume, and you can lock your volume. In fact, the volume is the only thing you can lock, as well as the number of moles of gas by adjusting the number of pumps. And that's basically it, okay? I think it asks you to show sample calculations in each one of these. And I don't even know if, I don't think there are any pictures that you guys need, because you guys are going to need the numbers from the simulator, okay? Are there any questions on this experiment? This experiment is basically just to demonstrate the ideal gas law, or how the different laws, the Boyle's law, Charles' law, Guy-Lussac's law, Avogadro's law, are all consistent with the ideal gas law. That's what this lab is about.